Okay, we're going to talk about continuity next. We say a function f of x is continuous, and by that I mean unbroken or uninterrupted, at x equals c if the limit of the function as x approaches c from each side is equal to f of c. To illustrate this, let's draw a picture. And suppose we have a function that looks something like this, and we're calling c our x value of interest, and f of c is the y value that goes with the x value of c. Okay, so the y value is f of c. Alright, so if we're talking about the limit, first of all, of the function as x approaches c, if I were to approach c from each direction, from the left, from the right, you can see that the limit value would be f of c. So the limit is equal to the function value. Okay? So that's when a function is continuous. The limit has to match the function value. We're now going to look at three discontinuities, or three situations where a function is not continuous. And we're going to classify them as either removable or non-removable. Okay? So first off, we have a hole. A hole is a situation in a function where you're moving along and you have a little gap, okay, a little space, or what we call a hole. This is a removable discontinuity. It's the only one out of these three that we classify as a removable discontinuity. Okay. To give you a quick example, suppose we have a function f of x and it's equal to x squared minus 9 all over x minus 3. If we were to actually take a look at the graph of that rational function, if you were to just put that right into your calculator and graph it, you would actually see something that looks like this. Okay? Now, you don't literally see a hole, but instead you'll see a little gap. Okay? Right here at 3. And if you were to zoom in on this, you would see that the y value there at that hole would be 6. So if we were to examine this a little bit further, if we were to factor this expression, x squared minus 9 is x plus 3x minus 3, the x minus 3's would cancel, and we'd be left with just x plus 3. Well, if we think about what's going on here, f of 3 on the original function, if I were to plug 3 into the original function, I would get something that is undefined. Or in your calculator, if you look in your table of values, where x is 3, it would say error. So that's if we were to plug in the original function. However, if you look at the function that remains after you remove a common factor, okay, think about why we're calling this a removable discontinuity. Think of it as we're removing a common factor. We're left with this x plus 3. Now suppose we wanted to find the limit of this function as x approaches 3 from each side. Well, if I were to approach 3 from each side, my height would be 6, and I can do that algebraically by simply plugging 3 back into this expression up here that was remaining after I canceled out my common factor. So the limit value would be 6. The function value is dne, doesn't exist, it's undefined. So since the limit value does not match the function value, we say we have a discontinuity. Remember what we set up above here. For a function to be continuous, the limit value has to match the function value. With this whole example here, the limit value is 6, and the function value is dne. So because these do not match, we have a discontinuity. So a hole is an example of a removable discontinuity. Next, we have a vertical asymptote. You've seen these before. This is a situation where you have a function that is approaching the VA that boundary line from each side, but it's never going to cross over. All right, it might look something like that. You could potentially have a situation where on each side of it, it's going straight up to infinity. All right, but you can see here that it's not continuous. The function value would not match the limit value. All right, the function value at a VA, it does not exist. And the limit value would either be infinity, negative infinity, or does not exist. Okay, so either way, it is not going to be continuous. Okay, just use common sense. You can see you're going along, and then all of a sudden it takes off and it's jumping way down there. Okay, it's broken. It's not uninterrupted. And lastly, we have a jump or a step discontinuity. Okay, this is where we have a function that's going along. Maybe you have a closed circle there, and then it drops down to an open circle and does something like that. It's a jump, it's a step. Okay, this is another discontinuity. Okay, so VAs and jumps, these are both non-removable discontinuities. The only removable one is the hole. Another explanation as far as why we call the hole a removable discontinuity can be shown in this example down below. This is a piecewise function. It's a function defined in pieces. We have this top piece where x is not equal to 0, and we have this bottom piece where x is equal to 0. Now if we were to graph this main function here using, let's say, our calculator, okay, what we would see is a line with a little hole or a little gap right there on the y-axis. Okay. Now if we were to actually factor this, okay, we can factor out an x up top. We're left with x plus 1. Notice that we actually have a common factor of x that we can remove. We can remove a common factor of x. Now remember, that means if you have a common factor, if you set the common factor equal to 0 and solve, you're going to have the location of your hole. So it should hopefully make sense to you that we have a hole at x equals 0. Okay, the common factor is x, set it equal to 0, there's your hole. Now what's left is this x plus 1 piece. Alright, so the location of this hole is actually 0, 1. If I were to plug 0 back into what's remaining here, I would have the y value for my hole. So if I plug 0 into that, we get 1 for the hole. Now notice we have the second piece of our function. They're telling us that when x is 0, the function value is 1. And let me just back up for a moment. With the first piece, if x were equal to 0, if we were to plug 0 in for x into this first piece here, you'd have 0 over 0. That's why they're saying x cannot equal 0. But by removing that common factor, we now have something left that we can put in to get a value. So notice with this right here, with this bottom piece, it's telling us the y value is going to be 1 when x is 0. So what that really means, what that suggests, is that this hole is getting filled. Or we say it could be removed. So it would actually just look like a nice straight line with no holes in it. Okay? So that's another explanation why we call a hole a removable discontinuity. So the bottom line is, you just have to remember that holes are removable discontinuities. VAs and jumps, which we also call steps, those are non-removable. There's nothing we can do about it. It's always going to be a non-removable discontinuity.